even better than the forged part. But the other technologies need to be improved as well. And yeah, this is the point. Limited quality, especially regarding the surface qualities, because the surface roughness is quite high. And generally speaking, above 10 microns, and that's why it needs post-process in order to mill or to smooth the surfaces, and is negatively affect the aesthetics of the product. Aesthetic tính thẩm mỹ. Improve manufacturing capabilities of the AM to integrate functional materials. Yeah. High machine scores. Yeah, this is one of the issues that limit the use of the AM in the industry at the moment, because I have mentioned to you just previously I have contact with an external company in America, and for one is called pressure regulators, which have the shape of, let's say, 10 centimeters, have 10 centimeter and 10 centimeter. So simply consider is a cube with 10 centimeters in length. So, but of course, it's not a completely solid structure, but with the small part like this, and each one, if it made of aluminum, silicon, tin, magnesium, and each part costed at that time 1,700 euro. So around 50 million Vietnamese dong. So which is quite expensive without the cost of post machining. Without the cost of post machining, just the 3D printing cost. So high machine cost and high material cost as well, because it's not easy to fabricate the aluminum's alloys powders. Not easy. Yeah, we think that it's easy, but it's not easy. How to store the material in the appropriate manner is a strict process as well. So you have to we have to carefully handle the powders, not only for the human health, but also for the qualities of the input material. So one of the reasons that the cost is really the costs are really high. Lack of knowledge and understanding of the environmental performance of the AM technologies. Yes, because for one issue, if it's under the development, and therefore this means that there's still a lot of knowledge that we have not known, and therefore that's why we lack of knowledge. Yeah. So like in the case of additive manufacturing, despite the fact that it have been developing for a certain period of time, but is far from being fully explored, and therefore yeah, that's the point. Limited automation, really? Actually, it's highly automated for the additive manufacturing, because once you provide the feedstock material, and then you set up the motor, yeah, and then just push the button, and that's all. The limited automation. Yes, because inside AM we have 7 subcategories, so I do not know which type of additive manufacturing they were mentioning about when they have written here limited automation. Yeah, it's hard to discuss about this, but okay. So let's come to the next, some advantages and challenges regarding the components and product manufacturing. I just want to highlight to you. And in the near future, if you have worked with the technologies, and you can easily see and you can easily find the disadvantages and advantages of technologies that you are working with. So let me focus a little bit on the product use. Yes, you have a lightweight product, so it has many uh, great significance. Yeah. When you subject these products to the utilization phase. Yes. Improve operational efficiency, sure. Improve functionality and durability, yes. And upgrade for product life extension, so for sure. This means that you can upgrade, you can optimize the part. So, in other words, after the upgrade, you can improve the performance, so especially regarding the product life. So the life can be extended. Yeah, it's simply like this. And the other challenge is regarding the uncertainties. Yeah. Uncertainty just means that there's a certain number of percentage of the parts after fabricated thing by the AM can work well, but the other they did not work well, and some failure occur. So, for example, the material delamination, the amount of voids inside the materials, or the material or the part distortion after the fabrication process, that they may occur for the 3D printed part, and what happened with them during the manufacturing process. So the researchers do not have the evidence to find the reason why is uh, this like this, and therefore it needs to be further developed in order to be ready to be used in industry, especially in the case of so for example, if it is used to fabricate the unimportant parts, so it's fine. It's just for decoration, it's fine. But it's for those who work with high safety factors, yes. So in that case, we must be sure about the performance of the part, to check it, to verify the part, to validate the part, yeah, before we can subject it to the market, the part to the market. Repair and manufacturing. Reduce the waste generation during the repair process. Yeah, it depends. It depends. Recycling. Okay. So I think it's too many points. And if you like, yeah, you can read more at home. Yes. So I would suggest you to remember 2, 3 points for each category. For example, product use, repair, manufacturing, and remanufacturing. So remember 2 or 3 points. So in case of needs, you still have some knowledge and understanding to answer the questions. So this is good to the approach. And when you graduate from the university, you may work with this technology. So at least you know the driving force to use these technologies. What is the promising applications? Yeah. And in which field that the AM can be used, to fabricate the part or to repair the part and so on, and how it can contribute to the future sustainabilities. Yes. And that's why researchers, engineers are doing quite hard at the moment in order to further develop the technologies. And the last line of this chapter showing you about the graph highlighting, so for example, starting from the ingot, thổi so until the time that until the point that we have the final part. So if you have the conventional machining or manufacturing, you have the buy to fly ratio, which is equal to 8.1. Sorry, 8 divided by 1. So the definition of the buy to fly ratio is the ratio between the mass of the starting billet and the mass of the finished part. So if the input material have the weight of 8 kilogram, so after the cutting process, so for example, we still have the part of 1 kilogram. So we eliminate more or less 7 kilograms. and 7 kilograms seen as the waste because we cut. So it cannot be cut in the form of the solid part, but it must be cut gradually, layer by layer. Yeah, this the limitation of the machining process. You cannot cut is like a blob, but you must cut it layer by layer. Uh, if the thickness cutting is high and the cutting tool can be damaged, or it can be fastly worn, or it even can be burned because the friction is too high. The friction of force is too high, and the tip or the edge or the cutting edge of the cutting tool can be worn or even be burned. So if the heat is too high and the heat can treat back the uh, the material of the cutting tool and reduce the strength of the cutting tool, reduce the hardness of the cutting tool, and is negatively affect the cutting efficiencies. And but here I just want to highlight that input material is 8 kilograms, for example, and the final part is just 1 kilogram. You waste 7 kilograms of materials. In other words, you do not save the money associated with the material. Yeah, and the energies which is required for the cutting process is also high. Yes, because you need to cut. But if you use the additive manufacturing technologies in order to fabricate the parts, and the part can be optimized during the design process, and then the input is no longer the ingot like this, but it's in the form of the powders. For example, it can be in the form of wire, and the input material is reduced. It is greatly reduced. So just around 0. So half kilo, around half kilo. But of course, because it's contain the support structure during the manufacturing process and after the manufacturing process, by additive manufacturing, you must eliminate the support structure because it's not necessary. It's not. We do not need the presence of the support structures. And after eliminations of the support structure, we have final pass weighing more or less 0.400 grams, let's say. And you have the buy to fly ratio is around 1.5 divided by 1. And yeah, 1.5 is great in saving the materials. So the material which invested for buying the material is greatly improved. Yes. So you save the amount of materials. You save the energies which is required to fabricate the part. And after the fabrication process, yeah, you save the energies or the fuel to run the components or the vehicle equipped with this part, because the total mass of the equipment is now reduced comparing to the upper case, and therefore we have the higher efficiency of using fuel. Yeah, and therefore it's better for sure. So it's clear for the first chapter where I introduced to you some fundamental regarding additive manufacturing and some basic principles, especially regarding the 7 additive manufacturing technologies that we have discussed during the first chapters. And now we have more or less 24 minutes. And let me show you the second chapter. Yeah, I'll stop here. Yeah, I like online teachings in terms of the fact that I can stay at home and work with you online. But then I would like to interact with students. So I would prefer a class to this extent so that I can discuss with you face to face. So I will uh, where is it? Here. So I believe that I already uploaded the chapter 2 on the RMS system. So I suppose that you could download the uh, the document for studying, even if you're studying on your own. You study on your own, no problem. Okay, so now we turn to the second chapter. Yeah, second chapters, where we consider the understanding methods for AM. So within the first chapter, we have learned several AM technologies, and there's wide range of material that can be used for different kinds of AM technologies. However, within the chapters and within the frame of the course, additive manufacturing, that I deliver to you, I just would like to focus on the understanding of the methods. Yes, and but I but it's up to you. It's up to you. If you want to study other materials for AM, so you are welcome to do. You are welcome to do. But you should know in advance the methods used for AMs, because why? For aerospace structures, so is generally speaking, is this is used to withstand extremely high load, extremely high load, even in the corrosive environment. So those environment that can promote the corrosion, so or the wear, and therefore normally it needs to be made of metallic materials, because metals, if the metallic parts can withstand the high load, and this is the first candidate material that should be used for aerospace industry, uh, if we use AM to fabricate. If we use AM to fabricate composite, yes, composite will account for, let's say, 40-50% of the material in an aircraft, but it is fabricated by another technologies, not the additive manufacturing. And if we focus on additive manufacturing, if we focus on optimizing the part structures, yes, to make to contribute to make the aircraft lighter, and then we should focus on metals, and AM and the structure optimization and the computer aided design. That's the reason that within the chapter 2, I just focus on the method for AM. However, in practice, there, yes, for example, you may remember about the VAT polymerization, where the input material is photopolymer. So it can also be used for sure. Slurry, concrete, yeah, ceramic materials, and so on. Yeah, good. So, student, you remember to check your attendance. So I will be happy that you know what you need to do. Yeah. So at least I discuss with you in English, so you understand what I talk to you, what I would like to convey to you regarding the course. The course is both aerospace materials and additive manufacturing, or in Vietnamese chuyên đề 2 I do not know how to call specialization. True? Okay, whatever it is. So now we have talked a little bit about the structures of metals, and it's just a reminder, because the main information is belong to the course of aerospace materials. However, Even in the course of aerospace material, we do not discuss in detail, in depth about the structure of matters, because the frame structures does not focus, does not describe that I must deliver the content to you. But basically, we have four phases of matter: solid, liquid, gas, and plasma. So plasma is the fourth form of the matters. This is actually the ionized gas. Yes, and it consists of different elements. It depends on whether it has the fixed position in the lattice structures or not. If it is solid, so you see that each atoms has its own positions. Yes, and under the influence of the heat, for example, so it means that the atom receives the free gift energies, so it can vibrate around, or it can oscillate around this equilibrium position. But generally speaking, the position is there. There's no. It tends to keep its positions at a fixed position inside the lattice structures. In the liquid form, yes. So the atom has not the fixed positions, and it has the shape of the device that is stored the liquid form of materials. In the gas phase, yeah, we see that the distance between the atom is larger comparing to the liquid phase. And in the plasma form, you have the ionized gas. Yeah, the gas is ionized. The elements consist of atoms. So the elements contain proton, neutron, and electron. We have studied um, during the 12th grade at high school. So I would not like to talk with you again the proton, neutron, and electron. Yeah, metallic elements. So generally speaking, is shiny, thermal and electrical conductive, or electrical conductions, able to deform. Yeah, ánh kim này dẫn nhiệt, dẫn điện này có khả năng biến dạng, vân vân. Metals consist many small crystals. Oh, it actually depends on whether this is this is the oh, I forgot. The metal can have several forms. This can be the how can I say the single crystal form. It can be the polycrystallized form. It can be the amorphous form, amorphous material, the vô định hình. Thì cái cấu trúc vô định hình thì thường chúng ta gặp trong polymer nhiều hơn, thế nhưng mà ở vật liệu nó cũng có cái cấu trúc vô định hình. Ngoài ra thì nó có cấu trúc đơn tinh thể và cấu trúc polycrystalline, nghĩa là đa tinh thể. Đa tinh thể thì cấu trúc gồm nhiều hạt, mỗi một hạt thì có cấu trúc phương mạng tinh thể xác định, đúng không ạ? Và khi mà cái phương mạng thay đổi thì người ta sẽ dùng để phân biệt giữa các hạt khác nhau, và cái vùng giữa các hạt đấy là cái vùng mà có phương mạng không ổn định, nó sẽ thay đổi, nó là cái vùng xô lệch của các cái hạt, vùng xô lệch của các cái cấu trúc, và tại vùng đó thì chúng ta gọi là vùng biên giới hạt, đúng không ạ? Thì vì nó xô lệch như vậy, nó sắp xếp không ổn định, không có trật tự như vậy, cho nên nó là cái vùng có năng lượng tự do cao và nó rất là kém ổn định. Và nếu như có lẫn các tạp chất xảy ra chuyển biến hay cái gì thì nó cũng phát sinh từ cái vùng biên giới hạt đầu tiên. Thế cho nên là khi mà các bạn học cái giản đồ trạng thái sắt carbon ấy, nếu mà phát sinh ra cái pha thì cái năng lượng để phát sinh ra những cái pha mới ấy, thì hầu hết nó nằm ở cái vùng biên giới hạt, bởi vì cái vùng đấy là vùng không ổn định, có năng lượng tự do cao, và không ổn định thì có xu thế là gì, là chuyển về trạng thái khác ổn định hơn để để giảm năng lượng tự do, đưa hệ về trạng thái ổn định hơn một chút so với trạng thái mất ổn định. Crystal, yes, the atom is in order in space, in the 3D space. The matter can be crystallized. Yeah, I'm sorry, this is the mistake. Crystalline in one of three structures. Yes, but we have more than three structures actually. Three common structures. FCC stand for the face center cubic, lập phương diện tâm. BCC stand for body centered cubic, lập phương thể tâm. SCP stand for closed package hexagonal. Đây là mạng lục giác xếp chặt. So the description, so the unit cell of the three common lattice structures are represented on the bottom right of this slide. So you can see that how the atom is attached to the unit cells. So the SCP structures, or some call the CPH, but they are the same, closed package hexagonal structures, face center cubic and body center cubic structures. The unit cell of the structures, this smallest group of atoms, because it's repeat in 3D. So instead of considering a lot of atoms, yes, in 3D lattice structure, so we just consider the smallest group of atoms having symmetry of cluster. Yes, so it's quite easier. So depending on the closed package plane, nó gọi là mặt xếp chặt, thì tôi nói về tiếng Việt thì có lẽ là dễ hơn cho các bạn, bởi vì cái mặt xếp chặt ở đây là cái mặt có mật độ nguyên tử xếp chặt nhất ở trong cái ô cơ sở, hay còn gọi là cái unit cell này. Thì đối với cả cái anh mạng lục giác xếp chặt chẳng hạn, đúng không ạ, thì chúng ta sẽ có mặt trên cùng và mặt dưới cùng là hai cái mặt xếp chặt. Đối với cả cái anh mạng FCC thì chúng ta sẽ có 4 mặt xếp chặt. Nếu như các bạn nhìn thấy con trỏ của tôi thì nó là cái mặt tam giác ở đây, đúng không ạ? Trên cái mặt tam giác nó sẽ đính 1, 2, 3, 4, 5, 6, đúng không ạ? Tương tự như vậy chúng ta có 1, 2, 3, 4, 5, 6. Và ngoài ra chúng ta còn hai cái mặt nữa theo các cái phương khác. Ví dụ đây 1, 2, 3, 4, 5, 6. Chúng ta có 4 mặt tất cả. So FCC, for example, structures has 4 closed package planes, and each has 3 closed package directions. So because it's form a triangles, so that's why these are 3 in each plane. In each closed package planes, we have 3 closed package directions, and these can undergo severe plastic deformations. Cái này thì hơi khó giải thích bằng tiếng Anh cho các bạn. Tiếng Việt ấy thì nó rất là đơn giản như thế này này. Trên một cái mặt xếp chặt là cái mặt có mật độ nguyên tử xếp chặt nhất ấy, thì vì làm cái mật độ nguyên tử xếp chặt nhất có nghĩa là cái lực tương tác với các nguyên tử nó sẽ phải là cao nhất thì nó mới xếp chặt nhất được, đúng không ạ? Còn nếu mà lực tương tác với các nguyên tử mà nó yếu thì nó sẽ tách rời nhau ra, thì nó xếp chặt nhất thì có nghĩa là nó sẽ bền nhất, và như vậy là biến dạng nó sẽ không xảy ra ở trên một cái mặt xếp chặt đấy đâu, mà nó sẽ xảy ra là giữa các cái mặt xếp chặt. Có nghĩa là khi mà tác dụng lực vào ấy, thì nó sẽ xảy ra cái sự trượt giữa các cái mặt xếp chặt đó. Đấy là chính là lý do mà tại sao chúng ta làm cho kim loại biến dạng được, bởi vì chúng ta tác dụng lực vào thì nó sẽ xảy ra cái sự trượt giữa các mạng tinh thể, thì nó là sự trượt giữa các mặt xếp chặt đó, thì nó có thể tạo ra các cái severe plastic deformation, những cái biến dạng dẻo rất là mạnh, đúng không ạ? Ghê. Cái severe này rất khó để dịch là tính từ, những cái biến dạng dẻo lớn chúng ta dịch nôm na thế thôi. Some meters polymorphous or allotropic. Cái này là các cái dạng thù hình, polymorphous hoặc là allotropic. So it means that some meters can be crystallized in more than one structures. So for example, the iron can be in the form of the iron alpha if the temperature is smaller than 912. Yes, because if you may remember the binary phase diagram for iron and carbon, but okay, some refer to 910. So some refer to 912, so it's okay, no problem. If the temperature is increased in between the 912 up to 1392 degrees C, and it exists the gamma iron. So these have the FCC structures, and delta iron have the BCC structures, as I already mentioned to you. When the temperature is ranged from 1392 up to 1539 and above, we have the above is the liquid form. Above is liquid form because it's melt at by 15,000 1539 degrees C. Grain structures. Grain structure is the larger order grouping of crystal. So each individual crystal line area can be considered as one grain, having same lattice orientation. So in between the grain, so two adjacent grain will have a two preferred orientation, and in between them we have can I say not clear defined orientation at the boundary regions. So that is the reason that the grain boundary generally accumulate crystal defects. Yes, because it's time not have because the grains boundary do not have the clear lattice orientation. So it has defect crystal defect. Microstructures is a structure of material observed at the micron scale, as you can see from here. As you can see the ruler showing the scale of 2 micrometers, or we say 2 microns. Yeah. So from this we can see uh, the size of the lamellar structures or the size of the grain. Each lamellar colony defining the grain, and each grain consists of a layer of brighter color and darker color. So, but here we do not know which side of material is. But you can click to the to the link below and see the description. Yeah. The crystal and the grain, generally speaking, not perfect. Life is not perfect. So it contains flaws and impurities. Yeah. Có những cái nứt gãy và có impurity giống như kiểu có cái tạp chất lẫn vào trong đó. So I just would like to show you the video highlighting how we sample for microstructure analysis. So it's just the preparation to be able to observe the material with the microscope. Có nghĩa là tôi muốn show cho các bạn cái video để người ta chiếu cái phương pháp chuẩn bị cái mẫu để soi cái tổ chức tế vi của cái mẫu đó dưới kính hiển vi. Thì stop sharing here. Where is it? Okay. Metallography. So this is a science of examining, determining constitution and underlying structures of constituents in metals, alloy materials. So just metallographic analysis is mean that you capture the microstructures of the materials. Yes, and the microstructures will have the influence on the properties of the part. And you can, with these microstructures, you can find a way in order to improve the microstructures to improve the qualities of the materials. So how to prepare the sample for observation? First, we need to cut into small parts. So absolutely, this is a destructive examinations. Cutting, and you need to mold. Yeah, it's very fast to talk. You need to cut into the small pieces and then you mold it with the polymeric materials, so that is had the shape, had the cylindrical shape, so you can easily hold it in hand, like during the grinding and polishing process. Grinding nghĩa là mài, đúng không? Mài bóng nó đi. Thì chúng ta phải giữ nó trong lòng bàn tay, cho nên là chúng ta phải gắn nó vào một cái khuôn nhựa để giữ dễ, để dễ giữ nó hơn. Thì trong cái bước grinding and polishing này thì người ta dùng nhiều các cái giấy ráp, giấy nhám, có cái độ hạt khác nhau để người ta tiến hành mài bóng cái bề mặt này đi. Và cái bước cuối cùng thì người ta sử dụng etching, có nghĩa là tẩm thực bằng cái dung dịch axit để nó ăn mòn bề mặt. Thì như tôi đang nói với các bạn ấy, nó ăn mòn xong thì nó để lại những cái màu sáng tối khác nhau ở trên bề mặt, bởi vì càng sâu càng ăn mòn nhiều, đúng không ạ? Thì cái vết lõm ở trên bề mặt nó càng lớn. Thì khi soi dưới kính hiển vi, đặc biệt là kính hiển vi quang học ấy, thì nó sẽ phân biệt được các vùng màu sáng tối, càng sâu hơn nó càng tối, càng nông thì nó càng sáng. Để từ đó thì người ta phân biệt cấu trúc giữa các hạt với nhau. Yes. So metallography is used almost on stage during the lifetime of components, just to check. It's for the material development, for the productions, for the manufacturing process, and control and failure analysis. So for example, during the material development phase, you need to analyze the microstructures to see which type of synthesizing parameters you can improve in order to enhance the qualities of the materials. During the productions, so the manufacturing process can influence, so can change the properties of the materials. Why? Because the heat generated during the manufacturing process, yes, the heat can be created during the cutting process, during the heat treatment process. Yeah, can modify the properties. Why it can modify properties? Because it change the microstructures, and therefore it modify the properties, and it need to be controlled, to guarantee the quality of the part after the manufacturing process. And the failure analysis. So because during the operation phase, there's many factors that can influence the performance of the part. So for example, the temperatures, the external loads, the environment, for example, the humidities, or the substance which promote the corrosion process, everything. And these factors will modify the microstructures and lead to the failure. And therefore, in order to examine which caused the failure, so we need to examine the microstructures. And something happened with the microstructure which caused the failure. And that's why we need to examine the metallography or the microstructures in order to, yes, guarantee that everything is controlled. Yeah, this is just policing process. Yeah. Using water, using the policing devices, and then clean. As I remember, they use acetone in order to clean. Ah. Come on. Yeah, it's the end. Yeah. It's the way people prepare the part, or we call sampling, in order to to be able to observe the materials, or with the optical or scanning electron microscope. So of course, with different microscope, you need different technologies in order to prepare samples for the observation process. But here, you see that is just the preparation for the observation with the optical microscope, optical kính hiển vi quang học. So I think this is enough for today. Yes, because I'm so tired as well. So hopefully that you enjoy the lecture, and I take these opportunities to wish you all the best in the new years, and enjoy your test holidays, and see you after the test holiday. And again, I'm here until the 3:35. If you have any question, just ask me, and I will be here to take your attendance. Yeah, thank you for the attend. Thank you for your attentions, and goodbye. Okay.